Got it.
Thanks.
All right. Thank you all for inviting me. It's a pleasure to give a talk and another number theory seminar. Sorry, and a number theory seminar. I don't do it that often actually. I haven't had a chance to give a talk in the last year. So if I'm a little rusty, I apologize. But I did just I sat in on a couple of master's vivas today, and yesterday. So hopefully I remember the things not to do a little bit more easily. So yeah, I will talk about Vinogradovs and value theorems, which was this big program spanning from about the 50s until just a few years ago, 2015. Well, that's when the big conjectures were solved. And I'm going to talk about what to do after it. So what have people been doing sort of since then? And in particular, what have I been doing? That's sort of just an outline of how the talk will go, right? I'm going to couch the Vinogradov mean value theorems in terms of Waring's problem, which I think is the most friendly place to start. So let's move on to that. So Waring's problem is actually what, 3.5 centuries old, 3.5 centuries now old, and it's the following assertion: you can write every natural number, so every positive integer, as a sum of at most 4 squares. So I'm allowing, when I say that, I'm saying you can have zeros, like you can have 0 squared, representing your number. And so like, for instance, 2 would be 1 squared plus 1 squared plus 0 squared plus 0 squared. So that's what I mean by at most 4 squares. Or you can write every natural number as 9 cubes, the sum of 9 cubes, the sum of 19 biquadrats, which is the old term for 4th powers, and so on, sort of famously wrote and so on. And what does that mean? What is Waring's problem actually supposed to mean if this is something that was asserted in 1770? Well, the general interpretation is that if you take any large integer, if I take any degree k, right, 2, 3, 4, as these first examples are, then I can find some large number of variables, which I'll write as d sub k. That could be for squares, it's 4, and for cubes, it's 9, and for 4th powers, it's 19. But for 5th powers, it's something even bigger, and so on. And I can say that every large integer has a representation as a sum of that many kth powers, where again, I'm allowing 0 to be something and to sort of pad it out. And right, so that was an assertion made in 1770, somewhere in Oxford or Cambridge, and by the 19th century, Hilbert showed that you can actually do this. You can get every large number in sufficiently many variables, right? So I can't pick some gargantuan degree like 1,000,001 and then find an infinite sequence of numbers that aren't the sum of some number of 1,000,001th powers. That's an impossible thing to do. And it sounds almost a bit obvious, but remember, we're mathematicians and not physicists, so we can't just like make these claims. We actually have to back them up. And Hilbert was the first to do this. He had some very algebraic methods, and the bounds he got for the number of variables that you need were quite enormous. They're, I think, tower exponential in terms of the degree, right? So I'd have something like, if I want to represent every large integer as a sum of 10th powers, I would need something like 10 to the 10 to the 10 variables, or something monstrous, okay? It's one of these very, it's a constructive proof. You can get a number of variables out of it, but you're not going to be happy with it at all. So that was the sort of unsatisfactory answer to this question. And people kept working on it because in the past, I should have said, the sums of 4 squares theorem, that was due to Lagrange in the same year, 1770. And by the time Jacobi came around, we knew how the exact number of ways to write every number as a sum of 4 squares. It has this nice answer in terms of theta functions, and the theta functions tell you that there's some divisors. You can write each number, the number of ways to represent it as a sum of 4 squares in terms of divisors of that number. Right? But that's very different from, so that exact answer is very different from Hilbert's solution, which said that you had a representation. Right? It didn't tell you the number, it just told you that there was one for every sufficiently large number. So people wanted to know, all right, do I really need some enormous number of variables? When the degrees are small, I can get something quite reasonable, right? What do we really expect? And is there a better way to do this? Right? We're constantly looking for better ways to do things. And building on work of Hardy-Ramanujan in terms of partitions, Hardy and Littlewood sort of really reinstigated our understanding of Waring's problem and the progress that's been made towards it for over the past century. So what they did is they introduced their famous tool called the circle method, which I'll describe in a moment. The circle method told us that you can write every large integer as a sum of a relatively few number of variables. This is a sum of that many kth powers. Right? What the bound Hardy and Littlewood got was not tower exponential, it's just exponential. Whatever my degree is, I can write it as the degree times roughly 2 to the degree. Okay, so it's basically something that's like 2 to the degree. So exponential rather than some tower bound. And they, not only that, they didn't just say that we have an existence, they gave an asymptotic. So as n is increasing, as your number is increasing that you want to represent as a sum of d kth powers, they told you that there's this asymptotic formula for it. And this asymptotic formula for it actually has a very beautiful interpretation. So it comes from the Adels. On the one hand, you have an Archimedean volume right here. This term depends very clearly on the number n, right? So if I want to represent a billion as a sum of squares, then as some number of squares, let's say it's 6, then it's going to be roughly a billion squared times this Archimedean factor, this gamma function factor, okay, which is quite explicit. But altogether, with those two things combined, those are really just the volume of a certain sphere, the real volume of a certain sphere, okay. And on the other hand, there's a lot of arithmetic that comes into play. So for each number, if you think about, well, why is Lagrange's theorem you can do every number as a sum of 4 squares, and I haven't said, well, can you do every number as a sum of 3 squares? Because you can't. And 7 is the first number you run into that you can't write as a sum of 3 squares, right? You try and do that, and you can't. And then you find out any number congruent to 7 mod 8, you cannot write as a sum of 3 squares. So these right here, these p-adic densities are what incorporate the arithmetic information like that, what's happening at the congruence levels. How many solutions you have, mod 8 or mod 1,000,000 or mod whatever, right? And it's not an asymptotic like we normally think about it, because this factor can fluctuate with n, this product of local densities, but it fluctuates in a very bounded way. If I fix the degree to be 2 and say the dimension is there's at least 10 variables, then that number is always between 100 and 1 over 100. So it's very squeezed in terms of what it can do. It's actually much better than that. It's probably like 5 and 1 over 5. And so you actually get a very satisfactory answer. This is asymptotic in the sense that the difference of these two sides, the number of ways to represent it, and this interesting expression on the right, has some order of magnitude that is a smaller degree in n. So in particular, the difference, if I were to write this and look at the absolute value, this is less than some smaller power in n, okay? It's smaller than that main term of n to the d over k minus 1. So that's what I mean really by an asymptotic. And this is a pretty satisfactory answer, all things considered. The exception that, you still, if you're someone in analysis or analytic number theory, you're really thinking, okay, is this number a variable? Sure, right? Can I do even better? Then if you take, for instance, k equals 2 again, and I say I need at least 5 squares, and Lagrange's theorem said that you only needed 4. Okay, so the game has been since then to try and find the best number of variables you can to satisfy Waring's problem. Right, so how do they do this, and what does the circle method Well, the circle method is this an incredibly powerful technique, right, to study diaphanting equations. And its starting point, at least nowadays, is really in this formula. Okay, I'm going to write the delta function, which is just the function that's 1 at 0 and 0 everywhere else. I'm going to write that in terms of an oscillatory integral, just this one right here. Okay.
Sorry, Kevin, but just when you lean back, sometimes your mic sounds a bit weak, I guess. So, I mean.
Oh, okay. One moment. Right. Is the mic here? Yeah, I'll lean forward like this. Is this okay?
This is better, yes.
Is it good enough? I can switch to the phone, but it'll take me a moment.
No, I think it's fine.
Okay, cool. Thank you for telling me. Sorry, so I'm not sure what people missed. Let me just back up a moment. So I was just saying the circle method is this really useful analytic technique, right? And it's useful in counting and getting asymptotics for the number of ways to represent a number, or equivalently, the number of solutions to diaphanting equations, or a fixed diaphanting equation or system of equations. And it starts by writing this delta function in terms of an oscillatory integral, right? So this delta function is just 1. 0. Okay. So what it'll do is it'll pick out a criterion for us. We'll be able to write an equation down as the difference of two things, and we want to know when that's equal to 0. That'll tell us when these two things are equal. All right, and that was their insight, was to do that, but they didn't do it in quite this way. They actually used Cauchy's residue theorem to get a complex analytic formulation of this. But Vinogradov saw that you can really do things this way, and it's sort of become the standard since. So you can rewrite your counting functions as these oscillatory integrals of exponential sums. And for Waring's problem, here's what I mean. So this buddy right here is just the number of ways to represent something. So it would be the number of ways to write an integer n as a sum of d kth powers. All right, that's all it's doing is counting. On the right, I actually look at the sum over every as a sum of all kth powers. And then I just pick out the ones whose sum gives me n. That's what this oscillatory integral does right there by exploiting this sort of thing. Okay. That's all it does. And so you're thinking, all right, great. That's pretty simple. What's the difficulty? Well, it's a great starting point, but there's still quite a bit of work to do. You actually have to understand what this exponential sum looks like. This exponential sum turns out to have very big peaks. If you want to plot it, as it's a function of this t variable, as I've written it, and t because if it wasn't clear, e of t is e to the 2 pi I t. All right, and so this is periodic from 0 to 1, right? Or 1 periodic, and this has peaks, for instance, when t is equal to 0. So if t equals 0, I'm actually just summing up everything inside of this box. And that would be of size n to the d over k, which is a lot bigger than my main term of n to the d over k minus 1. All right. But that actually is only true in a very small window near t. The window of size actually 1 over n. So that you pick up the right amount of mass, that d over k minus 1, n to the d over k minus 1. But what happens at t equals 0 isn't the only thing. It's also what happens at t equals a half, t equals 1/3, 2/3, 1/4, 3/4, and so on. Basically, all the fractions of low complexity or small height. You can get asymptotics for what this exponential sum looks like. You can rewrite it in terms of Gauss sums or Weil sums times some oscillatory integral. And when you do this, you end up getting this process of major arcs and minor arcs that Hardy and Littlewood introduced. It didn't come up, I think, in Hardy and Ramanujan work because everything happened to be a major arc there. And actually, for degree 2, everything is still a major arc. But as soon as you get to higher degrees, you really need these minor arcs. And these major arcs, the way I think about them is they're sort of low frequency information. They're And in contrast, the minor arcs are high frequencies. And the high frequency information is something that oscillates quite a lot and is basically noise. It cancels itself out. But these major arcs have all the content. They're going to be what gives you the asymptotic. Okay, so without going into sort of the technical details of that, I just want to show a couple of pictures to give you an idea. So this picture is, I've done that exponential sum when the degree was 2. I sort of plotted those values when at a certain scale. So this would be, I go up to moduli 100 and I look at about a window of about 1 over 200. And you see there's this big peak at t equals 0, like you expect. All right. And then there's other peaks at these rational points in between. Well, surprisingly, there is a bunch of cancellation at t equals 1/2. That's not too surprising, actually. But then you see other things around 0.3, or sorry, 1/3 and 2/3 and so on. And if you do you zoom in, you do some more resolution, you look at more moduli, a bigger exponential sum at a smaller scale, then you'll find that, okay, you still have that peak at t equals 0. And then you sort of see more of this behavior popping out, right? This is sort of what was there before, but now you've got also more fine scale information in terms of these other things down here. Okay, and it really, those frequencies are what's picking out the arithmetic behavior. That gives you the singular series, those p-adic densities I didn't really discuss a whole lot of. So I find this picture pretty helpful to see what is happening. It's sort of a frequency portrait of what's happening for sums of squares. Okay, it's just a one-dimensional version. I just looked at basically the sum n equals 1. In this case, I guess 10,000. Yeah, e to the t n squared. Okay, and yeah. So just to give an overview of how you use the circle method and how you go from there. In order to tease out this information from the low frequencies of the major arcs, use Poisson summation or some tool like that to get these asymptotics. And that's great. That works pretty well in a few variables. And the real difficulty happens to be those minor arcs, what's left over. And the way those are often controlled, or one of the simpler ways, is to use Weil's inequality. And that just gets you bound on the whole norm, sort of away from these low frequencies, these major arcs. But the bound coming from Weil's inequality is quite poor. And that's what makes you need a lot of variables. The way around this is to actually get mean value estimates, which are almost the size of things that you want. Okay, and that is what we're going to be getting to soon. So are there any questions at the moment? Sort of high-level overview of Waring's problem. I'll just take a sip in case there is one.
I do have a question. Is there a conjectured value for the minimal d?
There is, and it actually depends on whether or not it depends on the degree for certain. I think I forget if the degree is even, it's one thing, and if it's odd, it's another, or maybe it's if the degree is in power of 2 or not. But roughly, what you should expect is you should be able to do it. Okay, if the world was working in your favor, the whole universe, then you expect to get it as soon as you have one more variable than the degree. In reality, it's going to be more like 2 times the number, 2 times the degree, as soon as you have twice as many variables as the degree. And there's a very good reason for why you would hope for one more variable than the degree, and that's a volume computation. Basically, oops. If I were to, so let's look at sums of squares, right? I'll think about, if I have a sums of squares, it's looking at the integer points on a certain sphere, right? Say this circle, supposed to represent a higher dimensional sphere. And okay, I can look at that one, I can look at the next one, the next one, the next one, and so on, right? Until I'm in some big ball. And we know how to count the number of lattice points inside of a ball. That's basically the volume of the ball, right?
Mm-hmm.
So if I'm writing some number as a sum of a number of squares, so say this is 1 to, yeah, I have d squares that I want to write each number as, right? That's basically looking at the integer points on a sphere of radius root n, right?
Mm-hmm.
Now, if I look at that same ball, sorry, if I look at the ball of that same radius, square root of n, there are going to be roughly square root of n to the d points
Mm-hmm.
inside that ball, lattice points, integer points inside that ball, right? So that would be n to the d over 2 integer points inside that ball. But unless there's some good reason for why there should be a lot more lattice points on a few spheres and very few on a lot of other spheres, you'd think they're roughly evenly distributed.
Mm-hmm.
And that's why you lose 1 power.
Aha.
Right? Because there are n spheres in there in a range from 1 to n. Okay.
Mm-hmm.
So that's just a naive volume counting estimate. And from everything that I'm aware of so far, that works. Yeah. So why would you expect at least d? Sorry, this is of course only true as soon as I have d greater than 2.
Yeah.
And in general, if I have kth powers, then this would be to the, n to the 1 over k, and the whole same argument just carries through.
Ah.
Yeah.
Then in reality, it's sort of like the double, no?
In reality, that's very hard. And even the circle method has tapped out. It can only do sums of 4 squares. We haven't been able to do sums of 3 squares. For sums of 3 squares, the only ways I'm familiar with how to do it right now is the sort of automorphic methods due to Duke, Friedlander, and Avaniet.
Uh-huh.
Yeah. But for 5 or more squares, Hardy and Littlewood, they sort of gave a new way. There were modular form methods that could do, I think, 4, 6, and 8 squares before them. Like Jacobi did, gave modular methods to do 4, and I think Hardy did 6 and 8, and so on. But then, yeah, for anything that's 5 or more, Hardy and Littlewood gave this asymptotic, and then they had some unpublished work where they did 4 variables, and that was generalized by Klosterman, who generally gets credit for that result.
I see.
But he makes it quite clear that they did the 4 squares in the paper that he wrote in his thesis. Yeah. Great. Yeah. Any other questions? I'll sort of trot along then. So just to remind everyone, the question I have right now is sort of how few variables can we do, right? I can't get degree plus 1 variables. I can't even get 2 times the degree. But there's this big program called, many of us call the Vinogradov mean value conjectures. But the people who are really working on that, i.e. Trevor Wooley, always refer to it as something like the optimal conjectures for Vinogradovs mean value theorems. But these are mean value theorems that gave a lot of progress on these bouncer Waring's problem. And instead of getting something like linear in the degree, it gives you something that's quadratic in the degree. So you get roughly degree squared over 2 variables instead, right? And this was recently solved. This was resolved basically in 2015, though it took a year or 2 for things to be checked and verified. So maybe 2016 is the right year. But it was done respectively by Wooley in the cubic case and by Bourgain, Demeter, and Guth for higher degrees. And I should say that for the quadratic case, sums of squares, that's somehow a classical result. Yeah. So what are Vinogradovs mean value theorems? Let's see how they're used, what they are. Before, we had Waring's problem, which was saying I have basically x1 to the k plus xd to the k equals n. Well, now we're going to symmetrize the situation and consider when I have d variables, a sum of d variables equals another sum of d variables, but each one to the kth power. And getting a good estimate for that are the mean value theorems that I alluded to before. That turns out to be quite hard to do with by itself, at least when k is bigger than or equal to 3. And a much better way to do this is, or a very efficient way to get at this problem, is to include all of the lower degree equations. So I'm not just going to consider this kth degree equation, which you can see is a homogeneous one, but also consider the k minus 1, k minus 2, and so on, all the way down to the cubic, quadratic, and linear, as indicated here. And the conjecture, there's a conjectured number of ways to solve each of these equations, right? So if I take all of my variables to be between 1 and n, then I expect there to be of order of magnitude, roughly n to the d plus n to the 2d minus this quadratic function of the degree. It's just k choose 2. Wait, k plus 1 choose 2, sorry. Up to some factors of n to the epsilon, which sort of just a safety net to give ourselves some room. Things you can think of as logs or divisor bounds, right? And those are expected, you're expected not to have these epsilon losses as soon as the degree is 3 or more, but it's actually necessary when the degree is 2. Right, so how does this relate to Waring's problem? Well, basically, you sort of enumerate over all the possible things that could happen for the lower degree equations in order to get back to what could happen at the top degree, for the top degree equation. Okay, so you would write that as a difference of these things. Let's say when they're equal to some number, let's say A1, A2, A3, and so on. And then you sum over all the possible values of A1, A2, A3, and that tells you all the possible things that could happen in this top equation. So I told myself to write that out, but I think this is sufficient. And what I'll do instead is write down how this is also an object in Fourier analysis. Why these are called mean value theorems. So if I take this exponential sum, let's write the two-dimensional case. So I take e to the n alpha 1 plus n squared alpha 2. I sum from n equals 1 to n, say. And I take the 2d power of it. I integrate that from 0 to 1 and 0 to 1. With respect to alpha 1 and alpha 2. This is exactly the number of ways, the number of solutions. Say M1, M2, N1, N2, between 0 and 1, such that M1 squared plus M2 squared minus M, oh, should say all the way up to D. My apologies. Let me just write that out real quick. Number. So M1 up to MD, N1 up to ND, between 0 and, between 1 and N, such that M1 squared plus M2 squared all the way up to MD squared minus N1 squared minus all the way down to ND squared is 0. That counts this. And why does that count? Why is this a way to represent that? Basically, I'll take D copies of this exponential sum right here. And since it's the absolute value of that squared, I take D of them as a product, and then I take D conjugated as a product, multiply all those together. That gives me this ASU value. And when you integrate with respect to alpha 1 and alpha 2, you have exactly this orthogonality condition that'll pick out those differences coming from the conjugations. Right? And similar things happen for, oh, I should have said also, sorry, M1 plus MD, SN1, SMD, also equal to 0. Okay. If I wanted to do something like pick out this equation being equal to some variable z, then what I would do is simply the same thing, but then I'll multiply it by e, let's say alpha 1 z1 minus alpha 1 z1 minus alpha 2 z2 d alpha 1 d alpha 2. And then that changes this to be z1 or z2 and z1 respectively. Okay. So this is the mean value theorem because you're looking at the mean of this exponential sum to some power. Right. And these bounds up here are as sharp as you can get with up to the factor of n to the epsilon. Right. We have lower bounds that say that is at least of this size. And I have these two, this as a sum because there's two different regimes. When I have few variables, that is when d is less than k times k plus 1 over 2, this term dominates. And when the d is sufficiently large, the other term dominates. Okay. And this term right here is coming from that volume estimate we just discussed, whereas this one actually comes from special subvarieties that lie on this system. And those subvarieties are where I just take x1 up to xd to be anything I want, and then y1 to yd to be any permutation of those first x variables. All right, and that tells you to get automatically into the d solutions in the system. But that's pretty small as soon as n is quite large. Sorry, as soon as d is quite large. Great. So finally, maybe a bit later than I thought, we're going to get back to, as I said, this program's done, it's completed in some sense. And so you can ask what to do next. And so you go back to Waring's problem. I told you we know the number of ways to represent a system of equations. And now you want to go back to that top equation. And we're expecting something like a linear number of variables, linear in terms of degree. But Vinogradov's program only gives quadratic, and so there's still a lot of room for improvement there. That is still open, even in the first non-trivial case of degree 3. Okay. You can now ask questions about restricting variables. So in terms of solving a system of equations like this, maybe I won't restrict to some sets. I just won't consider everything inside of the range from 1 to n. But I'll just consider primes, or I'll consider smooth numbers, or I'll consider just a generic random subset. And I want to get asymptotics, or at least good bounds, depending on the cardinality of that set, and not in terms of any particular structure of it. Well, that question actually was solved at the same time as the Vinogradov mean value theorem. So Bourgain, Demeter, Guth, and subsequently Wooley satisfied this or showed the best possible bounds you can get for restricted variables. Right, and that's really a reflection of the technology that was used to develop, or technology developed to answer this problem. It's called decoupling and harmonic analysis and efficient congruencing in number theory, developed respectively by Bourgain, Demeter, Guth, and Wooley. And it's a super powerful tool, which I won't get to today, but there are a lot of good talks online about it that you can look up. You can, of course, generalize things at higher dimensions, consider higher dimensional affine invariant systems of equations. The key property of why I'm mentioning this affine invariance now is that's exactly what is useful and why we can do things for Vinogradov mean value theorems that we can't do for Waring's problem. Adding in all those lower degree equations, I'll give you a lot more symmetries in the system to exploit. You can go back and do Waring's problem with restricted variables. So that's like a harder version of the first one. Right, but while these two are done, these other two are still open. And more generally, you can do non-affine invariant systems, more higher dimensional things that aren't affine invariants. And then more recently, what I've been thinking about, and others such as Trevor Wooley, Julia Brandes, and so on, and Sprodinsky, it's coming up in additive combinatorics, is subconvexity in Waring's problem. Sort of beating, when it's reasonable to, beating the bounds that come out of the Vinogradov value theorems. So these are useful beyond just analytic number theory, right? If you didn't care about counting solutions of diaphanting equations, maybe you would have cared about this because you're interested in getting zero free. You want to prove zero free regions for the Riemann zeta function. At the moment, this is the best we have is going through things like Waring's problem, or through the estimates we have for those exponential sums, which we study in Waring's problem. But then it comes up in additive combinatorics, PDEs, harmonic analysis, ergodic theory as well. So I wanted to get to I want to quickly go through some applications in ergodic theory, something that's been well studied at this stage, and really get to what I mean by this subconvexity in Waring's problem. All right, so I'll kind of quickly treat these unless there are any questions at the moment. Right. So to quickly go through the pointwise convergence, there's this thing called Birkhoff's ergodic theorem, which is a pointwise ergodic theorem. I take some measure preserving operator acting on a space, and I assume it's ergodic. If I have a nice function, which in this case just means L1, then I have these time averages converging to the space average almost everywhere. The way you should think about this, or at least the way I think about this, is you have something like n times alpha mod 1. If alpha is an irrational number, then translation by alpha happens to be an ergodic measure preserving operator. And when you look at n alpha mod 1, as n goes to infinity, and look at the set of points that happens, it equidistributes on the circle, right? That doesn't happen when alpha is a rational number because it gets trapped in these periodic suborbits. And that sort of explains to you why you get almost everywhere and not necessarily everywhere. Okay, so think about higher dimensional generalizations of that. If you're familiar with things like Felipe was just looking at with these hyperbolic manifolds, and there's certain dynamics there, homogeneous dynamics there that has a similar flavor to this, but it's much more precise. So that was done a long time ago, and there are higher dimensional ways to pursue this. You can do averages over a box or a big cube, or you can do something singular like averages over the boundary of a ball over a sphere. And in particular, you can do some other sort of, seen from an ergodic point of view, rather weird sets. You can look at averages along the squares. So these time averages, we're sampling along just at each time. Now they're going to sample over a sparse subset of square times. And it turns out that if you have a nice enough function, a little bit nicer than before, only a tiny bit so, then you get the same sort of convergence. And that generalizes looking at something like n squared alpha mod 1, where alpha is still an irrational number. So the higher dimensional version of this was due to Magyar, where he sampled over integer points on a sphere. And using the Vinogradov value theorems, myself with some collaborators, in particular Tess Anderson, Brian Cook, Angel Kumchev, we looked at sums of k-powers, and using those Vinogradov value theorems, the best work available, we can get about degree as many, we can prove these sort of ergodic theorems as soon as we have enough variables, and that means quadratically many variables. It's the same limitation that comes up in the Vinogradov value theorems. And that's for a degree, which is an integer, a positive integer, right? With Costas Poulias, we have been able to handle fraction. Okay. Also, Tess, Brian, Angel, and I were able to talk about sampling when your points are coming from primes. All the coordinates are prime or something like that. So these things, these go beyond the Waring's problem. Waring's problem asked about the number of points on a particular number of integer points on a hypersurface, such as a sphere. This now gets into the dynamics and the analytic properties of functions defined on those spheres and their integral points. Right? In particular, we have these discrete spherical averages right here. I take some function defined on the integer lattice, and I take at each point, I look at all the values, all the integer points that appear on it. I sample my function there and I take the average. That gives me a new function that I replace right there. Okay. And if I can control this in something called the Maxwell function, then you can start talking about these ergodic theorems. The way to do this is to look at the Fourier transform of this operator. When you look at this Fourier transform, it's a function, you start with a function on ZD, and that Fourier transform is out a function on the cogroup, the TD, torus. And it looks like, it looks like this. Basically, I plug in my function and I apply the operator and take its Fourier transform. That looks like the Fourier transform of that original function times an exponential sum that's been normalized by its number of points. And that's just a carrier, that is the Fourier transform of this set, or the function that defines this set, and vice versa. And so Waring's problem has to count the number of points on this. From my point of view of trying to understand the Fourier transform of this, the indicator function of this set, that's just the zeroth harmonic, counting the number of points. And the way you get at these other problems is you actually give an asymptotic, or a way to understand what happens at non-zero frequencies. And so Magyar, followed by Magyar, Stein, and Wenger, they actually did this for sums of squares. Right? And they gave something that doesn't look as nice as what Hard and Littlewood had, but it's necessarily more complicated. You still get a lot of features. You get something that, some Gauss sums that arise. These are calculating what happens at rational frequencies of low complexity or small height. You get this Fourier transform of the spherical measure, and you get some error term, right? You don't, the asymptotic, I sort of suppressed the error term, and this you really have to come to grips with in some way. And the work with other people was refining that Fourier transform measure, and then sort of standard techniques allowed us to go from there to other places. But this approximation formula really generalizes what happens in the circular method, and it has a lot of applications that were largely worked out by Ákos Magyar. All right. So that was done, or that's a few years old. And more recently, you can do things like extension estimates. I mentioned how I'm curious about what happens, or I've given applications for when I study this exponential sum, where I look at the integer points on a sphere and its Fourier transform. Now, if you take in and you wedge in some weights, if I can control the behavior for an arbitrary weight, then I can do a lot more with that. What can you do? In particular, you can do things like these green tau theorems, right? Or what are they called? Sorry, I'm blanking. These theorems in these Roth type theorems in additive combinatorics, or Zamorati theorems, right? You can start understanding configurations. The weights you throw in there are going to be weighted on certain configurations, and you can play these density increment or arguments when you have good bounds for these. And these bounds come out as, I have some norm for my extension operator, and I need to bound it in terms of the weight, right? If I take those weights and I multiply them all by 1,000,000, that multiplies everything by 1,000,000. And so I have to have some way to normalize that. And this setup right here at the bottom is one way to do that, right? It's more difficult to control than the unweighted bounds. So what does something like this mean, or this mean value estimate, right? When we looked at this, and I took P equal to 2D, then we said that that turned out to be that gave us something like M1 MT, in this case now on a sphere, just right as that, and N1 up to ND. It counted those 2D tuples such that M1 summed up to MD is equal to N1 summed up to ND. It counted this number, right? That's what this does. This right here, the weighted one, if the weight is, say, the indicator function of some set F, which could be a set of primes, could be something else, depending on your interest or your application in mind, then that is actually making you restricted to understanding the points here. Okay, I'm not just laying on the sphere, but I'm also lying in some particular subset as they lay on the sphere. So it's something that's much harder, right? I could restrict to a cap, I can restrict to a bunch of different things. But it is very useful for applications. And the extension problem for the sphere is actually still quite open. Right? This has applications again and for Roth type theorems and for dispersive PDEs. So having sort of gone through that a bit quickly, I want to talk about smoothing properties of these averages and how they relate to subconvexity. And I'm aware I only have a few minutes left. Right, so these are the averages right here at the top that I started with. Okay, again, I've taken my point in space and I take a big sphere and I look at all the integer points on there. And now I have some function defined on all of the space. And I just sample at the points on that sphere. I replace every center by whatever the average is over all the points on that sphere. And generally what we think happens in harmonic analysis is that this should smooth out your data somehow. If I know what's happening nearby and I replace it with an average of what happens nearby, then it should smooth out, right? A thing to think about here is the fundamental theorem of calculus, right? You can't be too far from your neighbors is basically what it says. And right, so I studied this question because Jim Wright sort of asked me about it many years ago. And it turns out it does actually improve in a very quantifiable sense that I won't get into. But Robert Kessler at the same time considered this question and proved, had very similar results. Instead, I want to focus on a simpler thing, a simpler question where I can write down what the diaphanting problem is a bit more easily. So instead of averaging over all the points on a sphere inside of ZD, which is some high dimensional object, I need at least 5 variables, so I can't imagine that right off the bat. But instead, I'm going to take a function defined on ZD, right? So just some function defined on the integers and doing something, all right? And I'm going to replace it by averaging along certain squares, right? Just a window of squares. And the question is, does this actually improve your data? We know historically that if I ignore the squares, I just do everything next to it, then it's going to make things a lot smoother. But if I have these big gaps now, these big jumps from squares, is that still going to happen? That's my question. And the answer is yes, actually. You get that it decreases. It mellows things out and makes them smaller. And that's written in terms of this particular estimate right here, which I don't expect to mean anything to anyone in the audience. And so I've rewritten it. Okay. What does it mean? It's sort of, I take a function on the integers and I look at this norm of it, this power of it. And I have that operator and this other power, and I get this relationship between it. The key feature, I'll explain this a little bit more in just a moment. The key feature, though, is that there's some dampening happening here from what I started with, right? I started with knowing this global information, and then I replaced this averaging operator, and the size of the averaging operator, it did get smaller because of this dampening factor. So in particular, if I don't consider all kinds of functions, I just consider functions where I take a set, your favorite set in the integers, a finite set though, and I look at the characteristic function of that set. It's just 1 on that set, 0 otherwise. Then it turns out if I look at, for each point in the integers, I look at all those squares such that x minus a square lands in my favorite set that I chose at the beginning. And I cube the number of ways to do that, add all of those up. It's bounded by the size of the original set squared times this factor of n. Okay. So it's somehow, you're thinking something that might actually be of size f cubed is actually of size f squared. Okay, because the size of f here can be much bigger than n is fixed. All right, that may not appear to be very interesting to people, but there's an underlying diaphanting problem that is pretty interesting. Turns out, if I want to prove this, all I need to do is bound the number of solutions to this equation. So m and n are going to be some integers between 1 and n. And I need to know how many ways can I write a non-zero integer z as m squared minus n squared. And that's pretty easy to do, right? We know that this is equal to just m minus n times m plus n. And this is a divisor type bound, right? If I let this be a and this be b, they're only n to the epsilon pairs of a and b. And by looking at a plus b, which is 2m, and b minus a, which is 2n, I can immediately pass back to m and n. So there's very few solutions to this equation. And that actually means this lightly motivated analysis estimate. All right. What my interest in is actually replacing this by another polynomial, say p of n, or better yet, a polynomial curve. I'll finish up in hopefully 1 minute or two at most, or a system of polynomials, p1, p2, up to p s of n. Okay. And so averaging along a curve. And when you do that, you do the same sort of thing, you end up getting systems of equations that generalize this one in the middle. But what that led me to realize is that compared to previous works in this area, due to Oberlin, Pierce, Kim, and so on, you really need to work with non-zero. This is super important, rather than zero. And that's sort of an essential insight that I had. So what is this? I'm going to show you a few graphs. Here's a graph where I looked at the number of solutions to this system right here for various z. So this is going from z up to, this is actually 10 to the 4. And so there's a ton of solutions when z is equal to 0, and then there's basically nothing else. I don't know if you can see, there's a little bit of blue down here. It's absolutely infinitesimal compared to the size of things at 0. Because if I just take m equals to n, I get a bunch of solutions for 0, and I get at least n solutions, right? Rather than n to the epsilon. But if I remove that one, there's a lot more structure that you start to see. Right, so that's me zooming in. I throw out this bad 0 value, and I start looking at what happens here. And if you go to higher things, you still get the same thing. But now, let me show you a 2-dimensional graph. And I'll stop after this in the next couple pictures. This is actually looking at solutions to m1 minus n1 plus m2 minus n2 equals z1. And then the same things, but squared. So again, when when m1, m2 is a permutation of n1, n2, you get that these two things are 0. The z1 and z2 are 0, and you get a huge number of solutions. But as soon as one of them is non-zero, you get basically what looks like noise, many fewer solutions. All right, just to show you a different profile of that, I removed 0, which is going off the charts, and these are where the solutions look like. And you can see there's a bit of structure to them. From a different profile, you can still see it. So there's a bit of structure. Somehow things are peaking along a certain direction. And understanding that is allowing me to extend things to higher dimensional curves. So that's where I want to end. If there are any questions, that would be an excellent time. Otherwise, I'll skip to saying thank you very much.
Thank you, Kevin. Let's open for questions then. Do we have any questions?
Surely I didn't explain everything that well.
Yes, so you have this shape. So do you have exactly what's going on? Do you have the asymptotics? You have n. So this is higher dimension. You didn't show it, but
yeah, this is higher dimensions. It's 2-dimensional now rather than, well, depending on how you count it. I'm counting 2 dimensions in terms of the number of free variables here, the Z1 and Z2. Right, and I just count the number of solutions for this, and that's what I plotted for Z1 and Z2.
I see.
And this gets really computationally hard to do, as you can imagine, because it's growing like quartically in terms of counting things, since they have 4 variables.
And the Z1 and Z2 you chose for this plot is what?
So I chose in this one right here on the screen now, I went up to Z1 being 25 and Z2 being 25 squared, so 625.
Okay.
There's a symmetry. If I take negative Z1, negative Z2, it's symmetric about that by just switching the M and N.
Oh, it looks like it sort of accumulates like that. There is sort of a.
Yeah, this point right here, I could say it. I know what it is. It's 24, 624 as Z1, Z2. And the number of representations is 99. In a window of, if I'm looking at everything, my M and N are going from 1 to 25. So that's the most. And I think if I take a windows of this size, right? So it grows, it's like X and then X squared. Then it always seems to be, well, actually I should write this as X squared minus 1 and X to the 4th minus 1. That always seems to be the peak as I look bigger and bigger. And the reason why to expect this is because those have, well, X squared minus 1 has 2 factors. That's going to give me some more solutions. And X squared minus 1 has 3 factors, which helps me have solutions. Basically, having factors helps me have solutions in this case.
Yeah. Yeah, in here it looks like if you fix Z, I mean, it's Z1 against Z2 squared, I guess, you're plotting it. So if you fix Z1 plus Z2 squared, it looks like there's sort of a symmetry. Yeah.
And that's Z2. Yeah, I agree. It looks like, yeah, it looks like there's some line right here, right? That there's.
No, I'm looking at the opposite, the orthogonal direction. If you look in the orthogonal direction, yes, it looks like it's made of several functions going this way as well. Like when Z1 plus Z2.
Oh yeah, it's like.
Yeah.
Yes. There's like, it goes like curves like this, right? It looks like that. I absolutely agree. For me, for that analytic problem I have in mind, what I really care about is I care about the worst value, and the worst value seems to cut across like that.
Yeah.
So yeah, it does seemingly have a lot of structure that I've only begun to explore. And I think the point I wanted to make was I came from a background in doing harmonic analysis, and we have a lot of questions we've asked on RD over real numbers, and you start asking over the integers, and some weird things can happen. And as far as I know, this sort of question hasn't been explored. But in sort of looking into it, it seems like there's a lot of structure there. And it's one of these things to do after Waring's problem, Vinogradov's problem. Vinogradov was all about getting sort of the right bound for this point. And now that we know that, that's the biggest signal. Let's throw the signal out and start looking at what else is happening. And it turns out you expect something much smaller. And I can prove things are much smaller in some special cases. And with Yulia Brandes, we've been able to, in some more cases, Shvarlinsky and collaborators have, and Wooley has as well. It's sort of I think of it as an emerging topic and trying to understand these subconvexity estimates. The subconvexity here is that this bound right here is a convexity bound, and it gives you the upper bound for everything. But subconvexity means that we're going to be beating that, right? And we expect to beat it by a substantial amount.
Let me see. Okay, do we have any other questions?
Yeah, just about the name, because I'm very familiar with the subconvexity bounds, but for L functions. And then that name comes because the proof of the convexity bound use some convexity principle and complex analysis. Where
Yeah,
does
this
the
one
name
is a little
come-
bit simpler in its origin. Basically, if I go back to something like the quadratic Vinogradov mean value theorem, I'll just write that real quick. I look at this integral, sum from n equals 1 to n, e n alpha 1 plus n squared alpha 2, right? And if I was looking at this, d alpha 1, d alpha 2, the Vinogradov mean value theorems were saying that this is always going to be at most n squared plus, n to the d plus n to the 2d, and then k times k plus 1 minus 3.
Yeah.
Up to some factor of n to the epsilon I don't really care about. Okay, now, if I add in this thing, e of, let me erase this, sorry. E of minus alpha 1 z1 minus alpha 2 z2, I still have d alpha 1 d alpha 2. Now, this bound still is true. It's still true because if I just apply the triangle inequality, that kills that right there, right? So this application of the triangle inequality is exactly what I mean by convexity. Now, what I'm beginning to suspect to be true is that when I plug in this thing and z1 and z2 are not 0, then I can get, this is times, I get the same thing as before, but times n to the minus 1. That's a little bit of a lie. That's only if d is less than or equal to 3. I think I mean less than 3. In fact, of course, as soon as I have more, this is just n and n squared, but I could add n cubed and so on. There's different values that come in here, and then I expect better bounds related to that. But basically, the point I want to make is when these variables here are non-zero, then I think I can save a fairly good amount.
Okay. I see. Yeah, I mean, in a sense, you can also argue that that convexity bound for L functions can also be consequence of applying the triangle inequality, and then getting subconvexity means that you want to somehow take advantage of the oscillation.
Absolutely, yeah.
But that's not the original proof, and that's not where the name came from, I think.
Well, you're right. It's not exactly where the name came from, but these are closely connected, right? Like yeah.
Cool.
I think there is a triangle inequality there that gets applied, and this one I think is just a bit more elementary than that.
So yeah, like I think nowadays that we have this machinery called the approximate function equation. Like once you apply it, then you have like a finite sum, and at that point, if you apply a triangle inequality, then you get what the convexity bound is. And for example, if you want to get subconvexity for a zeta function, that means getting an oscillation of n to the it.
Absolutely, yeah.
But I think back then was what you do is somehow The way I learned first time is you're supposed to think of it as a version of the maximum principle. So like if you take like a, let's say it's not entire, but let's say a meromorphic function on the plane, and you kind of control the growth in each vertical line, and if it grows like so in each vertical line, then like, if you know the growth
Yeah,
in two
if you
lines,
have
then
two
you
vertical
can,
lines, right?
yeah,
And you control it
yeah,
on one and the other. And
yeah,
there's a way to convexly control it on in between.
yeah. Essentially, the growth is a convex function. So that's like, okay, I was expecting for this like the word convex
That
in the explanation, but I mean, I'm fine with it. I'm just
that comes up in the analytic formulation of the problem that I kind of skirted past
no.
when you want to understand the averages
Mm-hmm.
and bound them that way. And in fact, so in the continuous problem that Stein studied for spherical averages, he proved a maximal function that did exactly this sort of thing.
Mm-hmm. Okay.
Yeah.
Anyway, cool. Thanks a lot.
Okay, any other questions? Okay, so let's thank Kevin again. Thank you, Kevin.
No, thank you all for having me. It's,
Let's finish recording.
I hope I entice someone to send me an email afterwards and chat more about it.
Mm.